Welcome to the Cosmic Pie Podcast, Episode 15, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Are you sure we're in North Dakota?
We are. It feels like it outside, too,
It
today.
does.
It was a little
It does
nippy.
today. A little nippy.
A little nippy. And
It warmed up nicely, folks. And then all of a sudden today it reminded us it's North Dakota.
yeah, did you see the forecast coming up here in a few days?
Be back up in the 80s.
Yeah, that's going to
So,
be amazing.
That's going to be nice.
So the first week in May is going to be summer-like weather here.
That's it.
We do have a live stream that's running, and if you want to say any questions or comments to us, we do have a chat feature associated with that. So please feel free to use that. We'll stop in the middle of whatever we're doing and answer your question the best that we can.
The best that we can and, try to keep it relevant.
But if you send it to us like 1 second before we're ready to finish for the day, we may not get to
We
it.
may not get to it.
That's happened in the past. That's why I mentioned that.
Okay.
Yeah. And also the disclaimer. You want to do that one?
Sure, we can do that. The opinions and everything expressed in this show are those of myself and Wayne and us only, not the university, not the state, just us.
This is going to be a weird podcast this time.
Yeah, I think so too.
I'm not feeling too well.
So
So we'll see if we can make it, number one, for the full hour, and number two, what we actually say in that hour.
yeah, sorry about that, folks.
We'll see how we'll play it back later when we're feeling well and judge it.
And make fun of ourselves.
Also, don't forget that we do have these podcasts uploaded on Spotify the next day.
Right.
So once we're done, it takes roughly about 12 hours or so to have the download file available. We're cheap, so we don't buy the premium YouTube subscription.
Yeah.
And so, it takes us a while to process the podcast and then put a thumbnail for the beginning card, if you like, and then dump it up on Spotify.
Right.
So that's what goes on there.
And any mistakes and glitches, it's because we're live. We're shooting this as it comes out. So
Shooting from the hip.
Yep.
All natural. And the other thing is that Robert and I never talk to each other unless we're on the podcast. Just kidding.
Just kidding.
But I mean about items related to the podcast.
Okay. Yeah, we don't discuss the podcast beforehand. So
And we want to keep it spontaneous.
Right.
Spontaneous combustion. That's the way to go. So, Robert, did you ever hear of the song that goes something like, I'm going to sing, okay? So
Okay.
some of you might want to mute it for a few seconds here. Lucy in the sky with diamonds.
That's the Beatles, isn't it?
That's the Beatles. It's also the name of a NASA spacecraft
Oh,
that
okay.
just recently passed by an asteroid in the main belt. The asteroid named, and let's see if you can think of, who do you think this asteroid's named after? Donald Johnson is the name of
Donald Johnson.
It's named after
Okay.
Donald Johnson. It's not like the asteroid's called Spartacus and it's named after Donald Johnson, or he named it or
Yeah,
something,
yeah.
right? Actually, the person who named it, that's, most of these asteroids have their name.
Probably should have been named Dwayne Johnson. Because it's
The
a
Rock.
Sorry, folks.
Pretty bad.
Yeah, that one was bad. Yeah, it was low-hanging fruit.
It was. Now, this spacecraft was launched back in 2021. Its purpose is to explore the Trojan asteroids. Now, there's a joke in there, which we won't go into. And you might wonder, what are the Trojan asteroids? Is it back in ancient...
Well, if I'm
Grease
not
time or something.
mistaken, I'm going to go out on a limb here because I'm not 100%, but I think they're in the Lagrange points ahead behind Jupiter in its orbit, right?
How would you know that when I wrote it on the slide, Robert?
You did?
In the bottom, look. Trojan. Jupiter Trojans are plus or minus 60 degrees ahead
At the
behind
L4
Jupiter.
and L5. Well, I could have read the slide. Wow.
Yes, in fact, the diagram that you see in the bottom right actually illustrates the position of the Trojan asteroids. They're color-coded in green, and the outer circle that you see there represents the orbit of Jupiter. So they follow ahead by 60 degrees relative to the Sun-Jupiter position.
Right.
Right, and behind. Those are the stable, gravitationally stable positions.
And notice that the L4 and L5, this is something a lot of people miss. They're not points. They're these lobes that are behind, so things can fall in and fall out.
Yeah, gravitational potential surfaces.
That's it. That's the word.
Equipotential surfaces.
Equipotential surface.
If you study that sort of thing in like physics class, you'll learn a lot about that.
You'll learn a lot about that.
And the other thing to note is it's not just Jupiter. Of course, every planet would have the same gravitational sort of regions, Lagrangian points.
Right.
So it's
that James Webb is in one of Earth's L4 or L5. Right?
Yeah, that's right. So, and the other thing is, people look for like asteroids, like bodies in our solar system like that get trapped through gravitational perturbations into these regions, and they get locked in those positions. And they actually move around, and they're not like in this like a circular orbit or elliptical type orbit. They actually meander around that zone, just like the James Webb Space Telescope and others that we have at our L5 position and L2 and L3 and all these other ones.
They kind of go into orbit around.
The central point. Yeah, exactly. So it's one of those areas where highly stable. In terms of a spacecraft, you don't have to do much maneuvering to stay in the relative position that you want to be in. So it cuts down on like thruster use and so on. So that increases the nominal lifetime of the mission. Yeah. So anyways, this mission is designed to examine those asteroids, but on its way, it flew by and will have flown by 2 of the main belt asteroid, and this is the latest one. So this asteroid, and you can see the image of it, was taken a close approach image just a few days ago, and it was the distance, the closest it got was about 960 kilometers or about 600 miles. Yeah. Now this particular asteroid has an average distance from the sun of a little over 2 times the average distance from the Earth to the sun. So we call the average distance, by the way, from the Earth to the sun as 1 astronomical unit.
Or 1 AU.
Or 1 AU. And this asteroid then has the average distance, or semi-major axis, as we would say, of, as you can read there, 2.383 AU.
Mm-hmm. And you're not fooling me. That's a potato.
Yes. And it puts it in the inner asteroid belt. Yeah. And as Robert alluded to, it has a shape that's very much like a potato. Yeah. In fact, it's roughly about 8 kilometers long and about 3.5 kilometers wide. And it's one of these asteroids that we call a contact binary.
So that's where 2 asteroids came into contact with each other. They were moving very slowly enough that their mutual gravitational attraction, I know that was a lot to say in one run, but they're sticking together due to each other's gravity.
Yeah, and you can almost vision that just by looking at this image. You can see the way it's oriented, that you have the one asteroid on the right and the other one on the left, and sort of a narrow connecting region between the two. And it's easy to see that, it looks like you just take 2 blobs of putty and stuck them together. And it looks something like this. So that's definitely the case. So interesting. Yeah. And of course, people are waiting, what's it going to be like when we get to the other, the Trojan asteroids? What sort of composition and shapes do they have? And will that tell us anything about their possible origin? Where did they come from? Right. Chances are they weren't in those positions initially in the early solar system, but actually ended up there.
I'd be interested in seeing how many of these contact type asteroids, binaries, there are, because the relative velocity in those Lagrangian points is going to be a lot closer, a lot smaller. And so I'd expect more of these to be happening, but that could be completely wrong.
The other thing is interesting is you take an object like this and you compare it, what was the ground-based data telling us about the shape of this object? Oh, yeah. And it looks like it wasn't exactly the shape that you see here. So it was off a little bit. And there's wide variation in the brightness coming from this asteroid, as you can imagine, given its shape. It's not, if it was a perfect sphere, right, then that's a lot different than if something is really highly elongated like you see here. So, I mean, there's improvements that need to be done in that type of analysis, but that's a good test of it is, what do you infer its shape to be, and then actually have a spacecraft that actually can measure it directly.
And how did we, I got to ask, how did we get that inference that what we thought was the shape, and it's due to photometry, looking at the light curve, how bright and dark it gets at various times. Right?
Yeah, and it's also related to what is the angle of the asteroid in terms of what part of the asteroid is illuminated from the sun, given the position of the Earth that you're making your observations from. All that, the phase angle type of situation. Right. All of that counts. It goes into modeling the intrinsic shape of the asteroid itself. And if there are any differences, or if you like something that doesn't quite work out, then there'll be a discrepancy between what you think it looks like and what it actually is
Right.
from direct in situ type of observations.
Because, as big as 8 kilometers by 3.5 kilometers seems to us, at the distance of 2.3 or 2.4 AU, so a little over 1 AU from us at its closest approach, it's still like 1 or 2 pixels on the camera.
Right, because then generally you're not going to get very high resolution, especially if it's ground-based. You get affected by the blurriness of the atmosphere. But you can use, the differences to refine your modeling procedures.
Right.
And then that'll just improve, other asteroids in terms of what you think their shapes are compared to what they really are in the future.
In the future, yeah.
So that's quite interesting. So there's a lot. I mean, you can imagine that we want to visit almost all of the asteroids in our solar system. It's going to take a while.
It's going to take a while. There's a few 100,000, almost 1 million.
Yes, thousands, tens of thousands of them.
Yeah.
So imagine that you can explore we use tiny nano probes or something, right?
Right.
And let's send out a cluster of them or something, right? And you got, I don't know, 1,000 of these little probes that get launched. And they're a little small, but they have, miniaturized electronics. They can send back some information like imaging.
Mm-hmm.
And you send them off on their way, and then you send another 1,000 and then another 1,000. It's like swarms of bees heading into the outer solar system to intercept these asteroids. I wonder how long it would take you to observe a large representative sample, like 50% or something like that.
And the answer is it's quite a while. I mean, if you could sample 2 a year, each of your little swarm, then if there's just 100,000 of these objects, that's still 50,000 years?
Well, the other thing too is you wouldn't want to do that per se, but what you probably want to do is which one of the asteroids have a potential of hitting the Earth in the future.
Right.
And go there first.
That's the ones you would that one and the ones that we believe to be metal for potential mining.
Yeah, and you want to know what is, as best as possible, composition of those near-Earth asteroids, Earth crossers, in case you have to institute some kind of mitigation system to, send them off in a different path or destroy them completely if you could do that.
Yep.
And that's that's something, in other words, you don't want to be caught with your pants down, as they say.
Right.
You want to be able to have this stuff surveyed and know exactly what we need to do in the future.
We know what needs to be done, how it needs to work out.
And that's always been the argument for a space program. And it doesn't have to be manned like as human rated, but at least have rockets that can go up there to get rid of the danger that would be posed by an asteroid that's heading our way.
Right.
And if you think that rocket, like the whole space program, is a waste of money, well, here's one case that you could sell it, right? Well, it may save humankind at some point in the future.
Asteroids, nature's way of saying, how's that space program going?
Yeah. I mean, luckily, in the past, it was a much greater incident of collisions with the Earth.
Right.
And if we didn't have any weather or plate tectonics or volcanism, you'd see a lot more of the impact features on the surface of the Earth.
Of course, we wouldn't be here.
Yeah, and we wouldn't be here as well. But I mean, if you look at bodies that are near the Earth, like the moon, look how many craters you see on the moon. And in the early days, like when we were just gearing up to go to the moon in the Apollo program in the 1960s, there was still, like, let's say in the 50s, before you send, robotic spacecraft to do some, like the surveyor mission and so on to do their work, that there was always an argument between, are those craters predominantly made by volcanoes or are they
volcanic or are they
impact craters?
Right.
And it turns out they're impact craters.
Right.
And there's a lot of them. And because the moon is close to the Earth, you can bet your bottom dollar that you'd have that sort of
you had that
impact
same level
happening
of
here on the Earth. Yeah,
Absolutely.
exactly.
In fact, you would have more because Earth is gravitationally and everything the other way is a bigger target.
Yeah. So at least in the distant past, I don't know how far you have to go back, a couple billion years, back to the period of heavy bombardment in the solar system, that the Earth was being pelted by these things on a regular basis.
Mm-hmm.
And luckily, that's not the case nowadays.
Now.
The last big one was, 66 million years ago, as far as we know?
Around 64, 66 million years ago. Yeah.
The event that we think linked with the disappearance of the dinosaurs.
And by the way, we have found that crater.
Yeah, the Yucatan Peninsula.
It's on the Yucatan Peninsula.
Yeah.
It's called Chicxulub. It's
Yeah.
centered near a little place called Chicxulub. And
in Mexico.
In Mexico. And you don't go expecting to see, this big hole in the ground. It's 65 million years worth of weathering and other things. And pretty much we have to analyze gravitational anomalies to spot it.
Yeah, it's underwater, and most of it, I believe.
Most of it is underwater.
And it's over 100 kilometers in diameter.
Right.
So that kind of an impact that would create that would be enormous amount of material. In fact, one of the byproducts of the material that was in the parent asteroid is iridium, and that's been shown to be deposited all around the world, essentially.
And on a nice thin layer and about the same time frame. So it came from somewhere.
That KT boundary, right?
Yeah. As we've discussed in the past, iridium is something that likes to alloy with iron. So all of Earth's original iridium was pulled into the core. And any iridium that is on the surface is delivered by asteroids, folks.
So it's external source.
External sources.
Scary.
Yeah. And we've got from Builder Mizuho Schwalm, sorry, got a bit behind, closest approach distance between what objects?
So this is between the Lucy spacecraft and the Donald Johnson asteroids, a main belt asteroid. The closest approach was about 960 kilometers. This just happened a couple days ago. The Lucy spacecraft is on its way to Jupiter's orbit to investigate the Trojan asteroids, which are located in the L4 and L5 position, which is 60 degrees behind and ahead of Jupiter in its orbit. These are relatively stable positioning. And people always wondered, we know it's populated by Trojan asteroids. I forget how many, but this spacecraft is designed to study their composition and their properties in detail. Basically looking to see if they're any different than sort of the main belt asteroids that we have.
Are the near Earths? And...
how do those asteroids get to those positions? Were they there at the beginning when the solar system was just forming? Are they latecomers?
Right. Are they captures?
Or, all this kind of stuff. And sometimes you can actually piece together which asteroids came from which parent body.
Yep.
I know there's a lot of work done on meteorites, for example, to try to explain where they actually came from initially. And people are always trying to go from chemical analysis to do that sort of connection.
And we're pretty good about that. And, I would be curious. Another thing I'd be curious about these Trojans is how many of them are actually comets? How many of them are cometary as opposed to asteroid?
Yeah, and that's kind of a tricky statement because as far as what we've seen, the history of the solar system, especially in the last couple decades, since the 70s, that sometimes comets look asteroid-like and sometimes asteroids look like comets now. There's not this clear discrepancy between the two. Good point. It's almost like there's a continuum based on the properties of the object itself, right? If there's a lot of sort of volatile type material that can easily vaporize near the sun itself, then that creates the cometary tail.
Right.
And we've seen that happen into objects which initially we thought were asteroids, so they got much closer to the sun, and then they turn into comets.
And then they outgas, and whoa, wait.
Yeah, so there is not that clear discrepancy then between those two. But
so I guess the more correct question is how many of them have high concentration of volatiles?
I think so. I think that's the better question.
Yeah.
And that would be interesting to determine for sure.
Yeah. So,
now, besides looking at asteroids in the outer solar system, that is, part of the solar system past us, one of the things just to update people on is the Dragonfly mission.
And
so the Dragonfly, and you want to explain what that's all about, Robert?
Okay, well, Dragonfly is a mission to send basically a flying rover to Saturn's moon, Titan, which is one of the largest in the solar system, and it's one of the few bodies that's not, in fact, it's the only body that's not a planet that has an atmosphere. And Titan has a very thick atmosphere. So you could easily make a little chopper that flew around in its atmosphere and then looked around at various locations looking for methane and ethane lakes, trying to collect some hydrocarbon rain and all these other little things, find out what the general surface features are on Titan.
Now, the pressure on Titan's surface is about 1.45 times that of Earth.
Right.
And that's different than what we're used to. We're used to being in environments where they're essentially at vacuum, like on the surface of the moon or on Mars.
Yeah, and I can think of two reasons for that. one, methane and ethane are, especially ethane, are generally heavier molecules than even Earth's atmosphere. Number two, it's a lot colder. And what do cold things do? They contract.
And the mass is a lot less than the Earth.
Right.
So the rain that's falling on the surface would rain slow rain coming down.
Yeah. Oh, it would, wouldn't it?
Yeah.
That's kind of crazy.
We just had a big discussion. I won't mention the person, but somebody did a thesis topic about human habitat on the surface of the Titan. Maybe I'll get a hold of him and see if he's willing to come on the podcast sometime. And this was just last week, and he was discussing in detail about what are the things that you need to do in terms of designing some type of a habitat module on the surface of Titan.
Right.
What are some of the unknowns? What are some of the known things? And that's part of it is the condition on the surface, since we only have the Huygens spacecraft that landed there many, many years ago as part of the Cassini mission when it went in orbit around Saturn. The Huygens took detailed imaging
Images
of the surface and sampling a little bit. But the Cassini spacecraft did detailed radar observations of the surface. So we know that there are lakes
and there are even rivers.
And quote-unquote oceans and tributaries of this type of material, right? There's hydrocarbons. So people wonder maybe Titan would be like the gas station of the outer solar system, that we could go there in the future and pump
Tank up and...
Yeah, but it's completely cloud covered in the optical. You can't see down to its surface.
Right.
And we knew that early on in the Pioneer days when we flew by, and especially in Voyager 1 flew by fairly closely to Titan and couldn't see its surface at all.
Right.
Which is why they redirected Voyager 2 to actually pass much further away. What's the point? If you can't see its surface, you can't photograph it.
Right.
So then it could set itself up for a trajectory to go on to Uranus and Neptune, which Voyager 1 couldn't if it flew close to Titan. So we kind of sacrificed Voyager 1 to get nice detailed imaging of the surface of Titan and didn't realize, I guess, because if we'd known, we wouldn't have done it, that the clouds are so thick that you can't see to the surface. Hence why you need radar.
Of course, we also got a good sampling of the rings doing that too.
Yeah,
so.
there was other positives, but we would have got more by sending 2 spacecraft past Uranus and Neptune.
Okay, yeah.
When you sample something once, okay. But if you sample it twice, you can then look for differences and why those differences happen over a period of many months.
True.
And that's kind of thing we were looking for.
So,
but anyway, so this mission, long in coming, right, to actually get back to Titan, and as you mentioned, it's like a helicopter. We've had, this same thing on Mars lately as an engineering test.
And it would not take as much lift because the denser atmosphere to move a helicopter of some sort around Titan.
And a smaller mass.
Yeah.
And so why it's in the story now is because the Dragonfly mission itself went through all the detailed review by NASA recently and passed. So now they're at the point where they can start constructing the vehicle.
Nice.
And it's set to launch sometime in July in 2020 on a Falcon Heavy rocket. It needs the oomph to get out to Saturn in a reasonable amount of time. Landing is scheduled for 2034. There's not an exact time yet on the surface of Titan.
Cool.
So I can see it going into orbit around Titan or something, or in orbit around Saturn for a while.
And then drop it off.
And making sure everything's ready to go and then drop it off.
Yeah.
The other thing is if you stood on the surface of Titan, you people vision like you could see Saturn in the sky, but you can't. The atmosphere is extremely thick.
Yeah.
So what you would see is like a brightening, like you do, like looking at the full moon on a really cloudy night. You can sense that there's the moon in that general location because it lights up the back of the clouds, and you can see that in the front, and that would be the same effect. But you'd never see this beautiful view of Saturn and its rings, unfortunately, because the atmosphere is just too thick in the optical. You wouldn't be able to see that.
Yeah.
So
now, I mean, I've got all kinds of questions about this. Are they going to power it with an RTB?
Yes.
Okay. Because
radioisotope thermoelectric generators.
Yeah.
So that's the only way you can really power things. And same as like a human rated habitable module. People try different things. We know the wind is a high velocity on the surface.
Okay.
And because it's fairly dense, it's like 98% nitrogen.
Mm-hmm.
So you don't have to. There's essentially no oxygen. So if you wanted to burn things, I mean, it's not like it has the the ethanol and the all of these hydrocarbons. You need the oxygen
But you
to
need an
combustion.
oxidizer.
Yeah, to see, and you got to be careful of that, right?
You're right. The whole thing goes up. Boom.
And so people thought about putting windmills on the surface if you have high speed wind
Yeah.
under that pressure. But then you wonder about the corrosive activity of the hydrocarbons, right?
Right.
Any type of carbon fiber or plastics that you might try to use, would that deteriorate in the corrosive atmosphere after a while, if that's the case? So
Yeah.
these are some of the things, the follow-up work you have to do, right, to study, to
So-
see what kind of equipment you want to bring there and what you need to do. Yeah. But it will be nuclear to start off with, for sure. I can't think, obviously solar panels.
Solar panels, and I was going to get to that.
It gets like even on the surface of the atmosphere of Titan, it's about 1/100th the amount of light
I was about to say, yeah,
as it is here on Earth.
the solar intensity at Jupiter's orbit is 1/5 of Earth.
And then you got the filtering effect of the atmosphere on top of that. So how are you going to use solar panels?
And
It's
the answer is
inefficient.
not.
No, it has to be nuclear. The only other way you could do is have some kind of, remember the talk back in the 70s by Gerard O'Neill, is famous for this. You'd have these big power stations in orbit around the Earth that would beam microwaves down to the surface. You remember that?
I remember that because I've often mentioned it, people. Yeah.
Oh, and people wonder what would happen if you accidentally flew through the beam in an aircraft. It's like a fly hitting one of those lights, right? Zap. And they thought maybe that'd be a cheap way of transporting energy to us, but that didn't pan out, or hasn't panned out, at least now. But could you do the same thing on Titan? You could have this big orbiter vehicle, right, that's generating electricity maybe through solar panels or some other way, and then beaming it down. But
and the answer is yeah, you could.
Is it cost effective?
Is it cost effective?
Yeah, that's always the question, right?
You're right.
Is it worth the money?
Is it worth the money and the effort?
Yeah, and probably the answer is no, it's not, right? But
easier just to do an RTB and run it for a year or two.
Yeah. So the good thing is that the Dragonfly mission has passed all of the hurdles, and they're starting to manufacture it. And you never know with federal budgets how they change. So hopefully this thing doesn't get canceled or something in the next couple of years.
And hopefully it won't keep changing design parameters so that it overruns and sinks web.
Yeah. Well, if you follow the history of it, like the spacecraft that flew by Pluto, New Horizon, that was killed and resurrected and killed and resurrected and killed. I don't know how many times. It was a lot. I don't know how these career scientists and engineers, take it, right? I'd be
biting my nails too much or throw up my hands and say, no, we're done.
You spend 20 years trying to get this thing, funded and launched, and you go through all these up and down. It's like it's enough to destroy you mentally, you would think, right?
Yep.
So anyways, hopefully this thing will be launched in 2028 and find success on its way to Titan and do a lot of interesting science.
That's it.
Yeah.
Okay.
Now, an interesting story that came out recently in the news that caught my attention is these objects called Magnetars.
Mm-hmm.
Now, I'm just trying to remember how long ago they kind of came in the forefront. I think it was in the 1990s that people started to talk
they were
about
known
these
about
type of
for
objects.
quite a while before
Yeah,
that.
they're quite a while. And what they are, as far as we know, are neutron stars with an abnormally very strong magnetic field. Now, it's not unusual to have neutron stars that have a strong magnetic field. As far as we know, all stars have some type of magnetic field. And the evidence of that, one of the ways, you look at the spectral lines, for example, on the sun, and through the Zeeman splitting, you can see that they're double lines. We have a high enough resolution.
Right.
And so you can see the evidence of the magnetic field. And we know, for example, a lot of the solar phenomena like sunspots and prominences and the plasma that we see and the different features are all related to ionized gas and its interaction with magnetic fields on the sun.
Right.
So our sun has a magnetic field, and we also see evidence for that for other stars as well. And imagine you have a high mass star that ultimately goes supernova and collapses down to form a neutron star. In a way, that magnetic field can be conserved.
Right.
And because you're dealing with a much smaller volume of space, the magnetic field strength on the surface of these objects tends to be a lot greater
Right.
than it was when the object was a star.
And If I'm remembering correctly, the magnetic field around a magnetar is so strong that you wouldn't have to worry about being spaghettified by the gravitational pull. The iron would just be ripped out of your blood by the magnetic field long before you had to worry about that.
Well, and the evidence for a strong magnetic field for neutron stars, of course, is through the pulsar emission.
Right.
So the pulsars were discovered in 1967, these very regular pulses of radio waves coming from a specific location in space. Ultimately, one was found in the very heart of the Crab Nebula. Mm-hmm. And we know that's a supernova remnant. Why? Because people saw it blow up in 1054, people living on the Earth at the time, right? And they indicated where the presence of a new star was in the sky relative to other stars. And when you go and look today, you see the leftover debris from the explosion of that star, what we call a supernova remnant. And in the heart of that is a pulsar. It flashes not only in radio waves, but also in optical light.
Yep.
In fact, there's this interesting story. I don't know if I told this on a previous podcast or not, but I'll tell it now. Pulsars were discovered in 1967. In the 1950s, at the McDonald Observatory, astronomers at the time were doing these public outreach events where you could say, like a Saturday, they would bring people to look through the eyepiece of the 200-meter telescope to look at various objects. And I guess one evening, the telescope was set up on the Crab Nebula, the supernova remnant, this leftover debris from the explosion of that massive star that happened in 1054. And a person was looking through the eyepiece at the telescope at the Crab Nebula and said that it was flashing. And the astronomer at the time thought, oh, it's flashing. That's called twinkling or scintillation, and that's due to and they started going off, I guess, telling this explanation of what the twinkling effect of stars is all about. And the person that was looking through the eyepiece, the woman said, no, this is not twinkling. By the way, for my day job, I fly cargo ships, commercial airplanes at night. And I'm always flying them at night. And I have lots of time to look at the stars. And I know what twinkling is. I see it all the time when I'm working. This is not twinkling. This is something else. Now, the astronomer who was on duty that night kind of dismissed it, never followed it up, just let it go.
Right.
It turns out that the pulsar that's in the Crab Nebula, it spins at about 30 revolutions per second.
Which is right at the edge.
Which is right at the edge of visibility of seeing pulses of light for for ordinary people.
It's that right at the edge of the flicker rate.
That you could see. You could think of the old monitors. You could see the flickering, especially in the corner of your eye type of thing. Yep. So she actually was seeing the flickering of the pulsar. And this was a full 10 years, a decade before they were actually discovered. So if the astronomer, and of course, hindsight's always 2020, would have followed that up, that comment, and then observed to see what was flickering, and they would have discovered pulsars. And the person who did discover it, at least half the team, got the Nobel Prize in Physics for that discovery. Mm-hmm. That was Anthony Hewish, and his grad student who actually spotted it never got the Nobel Prize.
Right.
Unfortunately, but that's the way it went. So we can't change the past, obviously, but we can change the future.
We can change the future.
Wording of those things. So these pulsars, then, by their very nature, are very strong magnetic fields, and that's related to the pulse phenomena itself. And we know that over time they get weaker and weaker as energy is bleeding off the system. They also slow down their pulse or their revolution. So the time between pulses is getting ever so gradually longer and longer and longer.
And you can see that happening too, because Hubble, one of its first things was to point at the Crab Nebula, and you can actually see the magnetic field of that pulsar sweeping through and bunching up and pulsating the plasma of the nebula.
You're probably thinking, are you thinking about the Chandra X-ray Observatory?
It may have been Chandra.
Yeah, it was Chandra that did very detailed measurement.
But it may have been Chandra.
It was Chandra. Yeah, they have a nice, beautiful image of Chandra.
And you can see it sweeping and mixing up this gas, this plasma in the nebula.
And of course, with atomic clocks, you can measure very precisely the time between pulses, and that's why we know they're slowing down. And that happens to all pulsars.
Right.
They're slowing down. And just at the rate you would expect in terms of the energy being emitted, coming from both the slowing down of the rotation of the pulsar and the weakening of the magnetic field in terms of the decreasing in the strength of the amplitude of the pulsation.
Yep.
So these
great stuff.
So these magnetars then are an extreme example of this, where they have a very, very high magnetic field, but they are associated with neutron stars. Now, this particular study on this magnetar people try to associate it with a supernova remnant. So if magnetars are associated with neutron stars, neutron stars
remnant.
are obviously associated with supernovae, right?
Yep.
Exploding of stars. Then that correlation should go hand in hand. The interesting thing about that, by the way, we do have an artist's conception of one of these magnetars. You want to go to the next slide, Robert, please? So this is an artist's conception, of course, showing the neutron stars in the middle, I should say, and the associated magnetic field lines. And you see the beaming effect that occurs. So at the magnetic north and south pole, the electromagnetic radiation can escape. If you think of synchrotron emission, where the charged particles are spiraling around magnetic field lines.
Right.
So you can beam emission along the magnetic poles.
Yep. Speaking of which, Bill and Rizzuto has also asked for this case is the source of the magnetic field motion, is the source of the magnetic field motion of electric charges are actual permanently magnetic materials.
Yeah, motion of the electric charges.
That's what I was figuring.
Yeah.
Too. Yeah.
So this is a magnetar. Of course, it's just an illustration, right? It probably doesn't even look like that, but you get the point, right? Very strong magnetic field associated with it. And if the alignment is such that that beaming sweeps across the position of the Earth, we see that pulse of emission.
Right.
So you think of it like a lighthouse going around and around and around. And if the Earth is in the right location, that beam of light will sweep by our position and we'll see that pulse. And then it goes around once and back again, then you see it again. So you see it over and over and over again as the thing spins around. And some of these pulsars have pulse periods on the order of milliseconds.
Yes.
That's the fastest ones, milliseconds.
In fact, they've got their own little class of objects called, millisecond pulsar.
Right, and they are so dense, right? They're extremely dense that rotation does not cause it to break apart because they're rotating too fast or something like that. That it's able to hang on to its material even though it's spinning around rapidly.
Yeah. Thousands of times a second, folks.
Yeah. Remember, you get an idea of the strength of the gravitational field on the surface. A good analogy that a lot of people like to use, experts in this field, is if you were standing, and you can't, but imagine you could stand on the surface of a neutron star. If you held out a baseball that's not moving relative to your hand, and then you let go of the baseball, by the time the baseball fell and hit the surface of the neutron star, it's estimated to travel at about half the speed of light.
Yep. That's just crazy.
The amazing when you think about it.
Of course, it would detonate like a nuclear bomb. A baseball, boom!
The problem in all that is how do you stand on the surface of a neutron star?
Oh, well, we'll neglect that.
Some days I can barely get out of bed.
Right?
Anyways, it's quite interesting. So the next slide related to this magnetar in particular is these observations that were done in 3 different methods, right? The one on the left that you see in the panel is taken from a Hubble Space Telescope in the near infrared at a centered filtered of about 1.6 microns. So this is with the Wide Field Planetary Camera 2. And the middle panel is observations taken at H alpha 6563 angstrom line. So for those who know, when you studied like atomic physics, like the model of the hydrogen atom back in, I don't know, middle school, I guess is when you first get exposed to it. You think of like the Bohr model of the hydrogen atoms and the different energy levels. The transition from the n equals 3 to the n equals 2 level releases a photon of this wavelength, 6563 angstroms, and it's a red photon. And because it's from hydrogen, and most of the normal material in our universe is all hydrogen, like 74% or so is hydrogen.
Right.
That, by mass that is, that there's a lot of hydrogen out there. And so you get a lot of situation where this hydrogen gets stripped of its electrons. It gets ionized by photons with wavelengths that are in the ultraviolet with energies like greater than, if you're into these numbers, 13.6 electron volts. Those photons,
that one gets drilled into you, folks.
Yeah, so you can ionize the hydrogen gas, and of course, the electrons want to recombine with protons, and that recombination, as the electrons descend down those energy levels, that transition from the n equals 3 to the n equals 2 level produces a red photon, and it's easy to see in the optical. So these emission nebulae then are very, very easy to see then with a telescope when you're operating at optical wavelengths. They look really red in color. So that's the light that you're seeing in the middle panel. The far right panel is observations taken at 21.1 centimeters. And if you also know the Bohr model of the hydrogen atom, and if you learn the fact that the ground state is not a single energy level, the n equals 1 level, it's actually split into two.
Yep.
One with slightly higher energy, one slightly lower. It's known as hyperfine splitting. And what we usually say is like sort of a simple classical view of this, if you like, is that when the atom is in a slightly higher energy state and the electron is in the ground state, the electron is spinning in the same direction as the proton, so-called parallel spins. And then, of course, the atom wants to be in the lowest energy state possible. So what happens is that the electron, if you like, flips its spin, now spins in the opposite direction of the proton, so it's anti-parallel spins, and that's in a slightly lower energy state. So that transition from slightly higher to slightly lower, that energy is released with the emission of a photon of about 21.1 centimeters in wavelength. So that's in the radio.
That's
so
in the
a radio
yes.
telescope would be able to observe that. You know, when that calculation was first made, they said the probability of that happening was about one atom. If you stared at a single hydrogen atom, you'd have to stare at it for like the order of 1 billion years or more in order for that transition to occur. So at first, when the scientists first discovered that from the Netherlands, he wrote a statement saying, basically, this is interesting type of thing that should happen, but we'll never really see it because who's going to wait around for that to happen? But of course, astronomers realize, wait a minute though, because hydrogen is the most abundant of all the elements, there are lots and lots and lots of hydrogen atoms. So at any given moment, there is a significant number of them that are flipping their spins, the electrons.
Right.
So you'll get this emission. In fact, with a telescope tuned to this wavelength, you can see the emission all over the place because there's so much hydrogen out there.
Right.
So observing at that wavelength is the panel that you see on the right. Now, what you see in all three panels is sort of this, we talked about comets before, this cometary tail, is the projected displacement of this magnetar with time, because there are observations taken over a long period of time. So you can work backwards to get some information about the proper motion, the relative motion of this object, you know, on the two-dimensional sky. And the modeling then will say, and of course it gets less uncertain the more back in time you go, projected backwards, where the object actually came from. What was the path that the object was on in the past to where it arrived today? So, and you see this done for the three different ways of observing. Now, the thing to note is, especially on the panel on the far right, the one taken at 21.1 centimeters, this is from the Canadian Galactic Plane Survey, notice the supernova remnant.
Right.
Okay? That's that extended source you see just above, what is that, a bluish type color or
Yeah. So
or teal
the
color
green,
or whatever it is?
Yeah, the blue
Yeah.
is longer in the further in the past. The red would be nearer, and then the green is pretty much up to date.
Well, no. So what you're seeing is all of them show projection, right, of the past trajectory and the spread of those uncertainties in the modeling to where it gets today, whereas the apex is where it is now because we know the precise location, right?
Right.
So where did it come from? Well, that becomes more uncertain the more you extrapolate it backwards in time. That's the spreading out that you see. But the thing is that in the 21.1 centimeter panel on the far right, you can actually see the supernova remnant that astronomers thought this magnetar, the neutron star, was associated with.
Right.
So if it came from the supernova remnant, then its backwards projected path should go through the middle of the supernova remnant.
Which it doesn't.
These are roughly spherical in size and shape, right?
Right.
And it doesn't. It's below it, notice, which means it didn't come
From that
object. It did. The progenitor of the neutron star
yeah.
did not produce that supernova remnant.
Can we project further back though?
It gets very uncertain, as you can tell, the spreading out.
Yeah.
There's not a lot you can do there. But this is enough projection backwards that you can tell that that neutron star was not at the center of that supernova remnant.
Yep.
So it is not associated like they thought with that supernovae. So whatever created this magnetar, either the supernova remnant faded away and it's not visible any longer, and they will fade away over time as they spread out and get more diffuse and get fainter and fainter, or something else happened here.
Well, here's a problem for somebody to come along and solve.
Yeah, definitely. So that's what makes this very interesting.
Yeah.
So we'll see how that goes. In fact, these supernova remnants, like the one that produced the Crab Nebula, you can take like an image that was taken, let's say, I don't know, last year, let's say taken with the Hubble Space Telescope. And then you can look at another image that was taken 20 years ago with the Hubble Space Telescope, and you can compare the size of the supernova remnant, and you'll find it's larger today than it was 20 years ago because it's constantly expanding outwards, right? Estimated velocities are on the order of about 1,000 kilometers per second, expanding in all different directions.
Yeah.
And so then you can work backwards in time and say, okay, how far back in time do I have to go so that the whole thing was at a single point? And it's about 1,000 years ago, back in 1054. So you can kind of test that, you see?
Right.
And it all seems to hang together. So we have a fairly good understanding of these supernova remnants. And this magnetar is definitely not,
From that supernova
based on
remnant.
all the evidence we have right now, is not associated with what created this supernova remnant. So where did it come from? Is it even a neutron star?
Right.
Is there more than one way to form a magnetar?
I was about to say, could it be a direct collapse? Like black holes we think happen.
Well, then you wouldn't see it, though.
Right. Well, I wasn't meaning it was a black hole.
Oh,
but
I
can
see.
you get a neutron star similarly by direct collapse?
Without the supernova,
Without
the
the
going
supernova
supernova.
Right.
Who knows? It's just
Right.
one of these oddballs. So,
That's
like I
it.
said, a puzzle and something that we need to solve.
Absolutely. So I'm guessing now we'll talk about Mars.
Now we'll talk about Mars. We haven't talked about Mars in a little while.
Yeah,
I
it's
want
been
to
a
just update people on an image that was taken just a couple months ago of the Curiosity rover. So this was taken by the Mars Reconnaissance Orbiter, I should say, which was in orbit around Mars. And you can see the track starting in the top right, sort of snakes all the way down through the middle. And at the bottom of the track, near the bottom of the image, you see that black object. That's actually the Curiosity rover on Mars. So we
Nice.
have the resolution in the Mars Reconnaissance Orbit to actually not only photograph the track, but actually photograph the rover itself sitting on the surface of Mars.
Now, let's be honest here. That thing's about the size of what, a big SUV, if I remember correctly.
Yeah.
So it's not exactly a tiny object.
But look at it. That's
But
pretty
that's
cool.
pretty nifty still.
Don't they say like spy satellites can read the license plate of a car parked on the...
They do say that.
I don't know if that's
I don't
right or
think
not.
that's right,
I
but-
question that a lot.
I mean, you'd need a pretty sizable objective lens or mirror.
Well, there's
to get the
there's
resolution
one
to do
thing
that.
there. Yeah, if you get it's something that works at the diffraction limit, all you have to do is pick the right wavelength and diameter of the telescope to get the resolution you need to do that.
Right.
But the other thing is you're looking through the darn
Murky
atmosphere. So I mean, you're going to have adaptive optics, and I don't think it's that good to do. I question that a lot.
Right.
In fact, the telescope would have to be so large
Right.
that you'd easily see it like the International Space Station streaking through across the sky at night, right?
Right.
What the heck is that bright light? Well, that's a spy satellite,
What?
So I wonder how much of that's true or not, you
Yeah.
see?
And but Mars, you don't have that problem, though, folks.
Yeah, you don't have to
because
worry
its
about the
is
atmosphere.
much, 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 much thinner.
Yeah, exactly. And those tracks will dissipate after a while because Mars does has wind
Does have
and has
wind.
dust storms and so on. So after many years, like a few million years, those tracks will all
Well,
be gone.
That's a neat image. I saw that not too long ago, where somebody was investigating the paths of dust devils, of dust storms.
Mm.
And you can see the tracks of the dust storms, kind of like these tire marks.
We actually had talked about that on a
We did?
podcast. Yeah, we
Okay,
did.
so it was
That's
podcast.
probably
That's probably where I was.
Yeah,
seeing
we
it,
did cover
because,
that.
But
But it was accumulated effect of many years of the
Yeah,
dust devils.
But you can see the trails where they march across the surface.
Yeah. So
That's
after a
kinda
while,
neat.
all these rovers that we send to Mars, when they die off and stuff, and if no one touches them, they'll all be buried under Martian dust eventually.
Yep.
Completely covered over, and you won't even know they were there ever.
Right.
That kind of stuff.
Unless you got a good metal detector.
Yeah, find them that way. But it's interesting. This image of the Curiosity rover was taken 4,466 days, Martian days, after it landed on Earth. And the Martian day is only different from the Earth day by 30 minutes, roughly.
Right.
It's a little bit longer by 30 or 35 minutes. So it's almost the same. So that's a long time.
So it's been there for 10 years?
Yeah, well, it's been there a long time.
Wow.
This is not the latest one was that Perseverance rover, right?
Oh,
So
okay.
Curiosity's before that.
Okay.
And it runs on nuclear power. This is our first one that had radioisotope thermoelectric generator using the decay of plutonium and to provide heat through a thermocouple to generate the electricity.
Yep.
And so it doesn't have to worry about its solar panels being covered up by dust. Isn't that nice?
Yeah, that's nice.
Because we've had that problem in the past
Right.
on Mars, so we don't have it here. Now, the big update.
Drum roll, please. There we go.
Now, last day we talked about this exciting, potentially, discovery of molecules in the atmosphere of an exoplanet a little over 120 light years away, K2-18b, right? Where scientists using the James Webb Space Telescope looking at its spectrum, and that's what you see here in this image again, we also showed this in the last podcast, detected the presence of dimethyl sulfite and dimethyl disulfite. Both of these molecules are associated here on Earth with
Life.
life.
Yep. Particularly plankton.
And there has been an argument that these molecules cannot be formed by
Abiotic non-living
process, non-living thing. So if you detect this, it's one of those biosignatures that everyone is looking for. Is there some unique set of molecules that you could find in an atmosphere that would be 99.9999% probability that it comes from biology rather than non-biology?
Right.
Any type of, some type of bizarre chemical processes under extreme conditions or something like that. So this is the one set of molecules that people had looked at. And so the spectrum of this exoplanet, even though it is of a poor signal to noise to say 100% confidence that these molecules have been detected, in fact, they're proposing to get additional observations with James Webb to try and prove that situation. Even if you had 100%, confidence and better data, higher signal to noise in the future, and it says, yes, indeed, these molecules are present in the atmosphere of this exoplanet. Does that mean that there's life on this planet?
Not necessarily.
Not necessarily. Well, of course, people want to look at that.
People want to look
And
at that.
as you'd expect, research has come out recently showing that indeed these molecules, at least the dimethyl sulfite, can be formed in abiotic processes. That is non-biology, non-life.
Shucky darn.
Well, we'll see. A lot of people are working on this hard now because of the implications of this new discovery, whether it means life or not. Have we detected life out beyond the Earth? So we will see.
This point highlights a comment I made last week, which is, I don't think there will be any one molecule ever found that will be definitive. Hey, this is a signature. This means life's there. It will be a suite of molecules. It will be several things in conjunction.
Until I see the golden arches appear over the horizon, when I'm approaching this planet, there's no intelligent life on that planet.
Yeah, you mean the Dollar General store setting up its yeah.
Actually, you could argue that if you do see the golden arches appear, there is no intelligent life on that planet. You think of the health effect of
Yeah, if
things.
you think about the health effects.
Anyways,
So
people have looked at this. In fact, they use, and we've had some people at the university that do this. I won't mention any names, but I know of one person in particular using quantum chemistry to look at these very sort of rare interactions that can occur in different environments. And this type of research is showing that, yes, indeed, you can form these type of molecules without having biology. The other interesting thing is this molecule has actually been detected on comets already. And also found in the interstellar medium.
Well,
that is the raw materials from which stars ultimately can form from. So if you find it in those locations,
that makes it highly dubious that it's due to life.
The interesting question is, under the conditions that can be found on this exoplanet,
can you form it?
Can you form it without life? And if you can't, and yet there's a huge abundance of it, way more than what we find typically on Earth, then is it pointing towards life?
Right.
That's the interesting question. So the first thing you need to do is, number one, get follow-up observations, very high signal to noise, to see if these molecules are indeed there. Because right now we're not 100% sure, and we like to make that confidence a lot higher than what it's presently at. And number two, explore all of the different ways that you can make these molecules without using life.
Right.
To see if it's indeed possible given the conditions that may exist, on this type of planet.
The concentration levels.
That's the important thing. How do you get to those in concentration levels?
Right.
Now, this planet is one of those ones that we think is completely covered with water. So any type of algae that would exist in that water, in that planet-wide ocean, then if there's a lot of it, could create the volume of these molecules that we're seeing. And the other interesting factor about this is that these molecules are relatively short-lived.
Right.
So it's not like they get made and that's it, and you can visit this planet 1 billion years from now and that molecule's still there in the same abundance.
It has to be being replenished, otherwise it photoionizes and devolves into simpler compounds.
Yeah, so that puts some constraints, where it comes from. The source then has to continually make this stuff.
Right.
So it comes from life. The life is still alive. It's not dead.
That's why I say a suite of, because you see things like methane and oxygen, molecular oxygen, and this stuff, then you start going, okay, you've got a lot of things that life produces that don't last very long. They have to be being resourced. What's going on here? Well, that starts pointing at life.
And the other thing to think about, too, is we know of over 5,000 exoplanets.
Right.
Take the instruments like the James Webb Space Telescope, point it at a few more of these planets that are similar, that are water worlds, and
see if you see these.
See if you see the molecules on those planets.
Good point. Good call.
So I'm sure that'll be done. It just takes time to do that. So that's interesting. There's going to be a lot more, I figure, in the next 6 to 12 months of research that's being done on this object. And of course, the next round of observations from the James Webb will tell us whether that signal goes away or whether it's there, but it's actually from some other combination of molecules. It's not from this. And that could change the story, of course, rapidly on that way. Okay. And then the final thing I wanted to talk about today is the search. It's a little bit, in some senses, off topic, but it's not really when you actually get into it. It's the search for something called a sterile neutrino. So we know there are 3 different flavors of neutrinos, one associated with the electron, one associated with the muon, and one associated with the tau neutrino. We know these neutrinos have a mass, a very tiny amount of mass, because they can oscillate into different types.
Right.
In fact, that was the explanation of the puzzle that we've had back in the 90s is when it was eventually solved by Raymond Davis doing an experiment in South Dakota in the homestake down in the mine, the old lead mine, I think it was.
Something like that.
Yeah, right now that's where they're building the Dune project, right? The deep underground neutrino experiment. And so he had a vat of chlorine, set up cleaning fluid, and as particles get released from the sun, in particular neutrinos, which is a normal release that happens in the thermonuclear fusion of hydrogen and helium, these particles interact with the atoms in the cleaning fluid and make them radioactive.
Right.
And then over time, you can just count how many radioactive atoms do you have. I think it was argon.
Particular type of atom, which gives off a particular color of light.
Yeah, I think it was argon. So it wasn't the light. It wasn't a Cherenkov detector.
I thought it was the Cherenkov.
No, he just did a brute force. He drained the tank every so often and literally counted the radioactive argon atoms that were in the fluid, and those were produced from the interaction with neutrinos.
Got it.
That's why eventually he wins the Nobel Prize. It's not easy work, right?
Right.
It's a lot of sweat. Now, what he discovered was that we're only detecting 1/3 the number of electron neutrinos coming from the sun. And you could make an adjustment for that by lowering the reaction rates in the sun so that you would only produce the 1/3 amount of electron neutrinos.
But then that blows up physics.
Well, that lowers the luminosity, the energy output of the sun, and it's no longer consistent with the solar constant, with the energy we actually measure here on the Earth from the sun. So you can't do that, right? So there's this big puzzle. Why are 2/3 of the neutrinos missing? And then from the theoretical grounds, they discover, well, if the neutrinos have mass, they can actually oscillate into these other types of neutrinos. The cleaning fluid method is only sensitive to electron neutrinos, not the muon neutrinos or the tau neutrinos. And once we realized that and had detectors that actually are sensitive to these other types, They're the missing neutrinos. So as the neutrinos travel from the sun, cross that 1 astronomical unit to reach the Earth, they oscillate into these other flavors. So by the time they reach Earth, on average, 1/3 of them are now electron neutrinos, which is consistent with the experimental detection rate. Okay, so we figured that out. But there's also the possibility of going beyond the standard model of particle physics. There are these so-called sterile neutrinos that do not participate in this oscillation. They do not interact with anything through the weak force. They only have gravity because they have mass. Okay. In fact, it's one of these dark matter candidates that people have looked for many years. Well, there are experiments out there that are running trying to detect whether or not these sterile neutrinos exist. And then from their properties and how many there are, maybe they are the dark matter candidate. Well, this is an experiment that just finished up lately, and it's the paper you see there on the panel known as the Prospect experiment, Prospect 1. And they were looking for sterile neutrinos using what's called the inverse beta decay. So this is related quickly. If you take a neutron, for example, you pluck it out of an atom and leave it by itself, it's unstable. It'll decay in roughly 15 minutes. And it'll decay into a proton, an electron, and an anti-electron neutrino. Okay. Well, if a reaction goes one way, as you know in chemistry, under the right conditions, it can go the other way.
Right.
So you can actually have the inverse happening, where you take, for example, a proton and an anti-electron neutrino, and out comes a positron and a neutron. So
so they were trying to detect the positron and the neutron pair.
So the idea was that in that reaction, then occasionally you would get a sterile neutrino that would be released. Now, I won't go into the details of this because we ran out of time and it's very complicated. But this experiment was running for a certain period of time looking for these sterile neutrinos, and none of them were discovered yet. So the search continues.
Search continues.
Now, if you're interested in this type of things, into astrophysics, science, astronomy, any STEM field, the arts, you name it, one place you could do is come to the University of
North Dakota.
And you can take classes both on campus and
online. 160 plus online degree programs, certificates, and courses. So
hopefully there's lots for everybody to choose from.
There's plenty.
Yeah. So don't forget, you always educate yourself,
right,
all the way up until the moment you die. Always be a lifelong educator. That's my sort of
beyond.
Motto. That's my motto. That's my motto. Now, our next podcast will be 1 week from today. That's May the 6th already. Boy, time is flying.
Time flies.
At the same time, 5 p.m. Central. And we always leave you with a quote.
Okay.
Now, this quote is related to
neutrinos.
Neutrinos, very nice. It's actually
I'm learning how you think.
It's actually by the person that proposed the existence of the neutrino to solve a little problem he was having related to the conservation of energy.
Okay.
And this is by Wolfgang Pauli, and he proposed the existence of what we later named the neutrino, which was named by Enrico Fermi. He proposed this new particle back in 1930, and it wasn't until 1956 that they were actually first detected.
Okay.
And here's what Wolfgang Pauli said about proposing this new particle. Quote, "I have done a terrible thing. I have postulated a particle that cannot be detected."
That it would be a terrible thing.
Anyways, if you like this podcast, please remember to give us a thumbs up. If you haven't subscribed, please consider doing so. And we'll see you next time. Thank you for watching.
See you next week, folks.